and welcome everyone to today's session of Seminario FLOTANTE. Our invited today is Henry Towsner from the University of Pennsylvania. He will be talking about hierarchy, VC dimension, and hypergraph regularity. So thank you very much, Henry, for accepting the invitation. And the screen is all yours.
All right.
Tamanho.
Thank you for
Senhor.
having me. It's one of the the small benefits of the pandemic has been being able to visit places virtually that would be it's much more of a to-do to visit in person. So I'd like to thank you for inviting me. So there's a bunch of words in the title, and I want to sort of jump into that with kind of stating the main theorem here, and then I should say that there's a lot of terms, and the goal of the talk is to tell you what the theorem means, since I don't expect that most people have seen a lot of these terms. But so let me talk a little bit about this theorem. So this is part of a project I've been working on with Artem Chernikov to kind of generalize, so that there were these results showing that ideas from classification theory like stability and NIP lined up with ideas in combinatorics relating to Seminario regularity. And there are generalizations of Seminario regularity to hypergraphs, which are the hypergraph regularity in the title. And Artem and I wanted to know, well, what can we lift the stability theory side, the classification theory side, to continue lining up with the hypergraph regularity side? And this was the first result in that of that kind. So what does this say? So we're thinking about this relation E, and we're thinking about it as a K-ary relation. And it's convenient to work in a K-partite setting. So there's just separate sets xi for each of the K components. But of course, you can think of E as being a K-ary formula with variable phi of x1 through xk, where again, we're sort of assuming that x1 and x2 have different sorts. So E is this K-ary relation, and it has small VCN dimension, and I will tell you what that is. And the theorem says that this means that there's an approximation of E. So for each epsilon, there's an E prime, which is close to E. That's what this second line says, that E prime is within epsilon of E. And E prime is simple in some sense. It's a union of a small number of n-ary cylinder intersection sets. And again, I'd better tell you what an n-ary cylinder intersection set is. All right, but and I'll say this again with text in a few minutes, but let me say that if K is 2 and N is 1, so E is just a set of pairs, and VC1 is just ordinary VC dimension. So this says when E is a binary relation with small VC dimension, and you could translate that to when E is a binary formula with as a binary NIP formula, then there's an approximation of E, which E prime, which is close to E, and which is a union of product sets. So a one-ary cylinder intersection set is a product set. And so that what I just said is what's known as NIP hypergraph or NIP graph regularity, and I'll write that down in a minute. But that's the line of results we're generalizing. I'm mostly going to talk about the case where K equals 3 and N equals 2. So that's the case where E is a ternary relation, and well, VCN isn't ordinary VC dimension, because basically all the new complications show up by the time you go one step higher. All right, so my goal is to just tell you what this theorem actually means, and then maybe convince you that if you'd been looking at the results Artem and I were looking at, this is exactly the thing you would have conjectured also. All right, I should make a small point about, I use this word small in the theorem, and small is of course not a formal notion. So there are two ways to think about what small VC dimension means. And one of them is, so that theorem, right, it was implicitly in a finite setting, because I was talking about cardinalities and ratios of cardinalities. But one way to make that idea of being small precise is to pass to a limit, which typically means take an ultra product of potential counterexamples. And then in the ultra product, small just means finite. And then these approximations have to be in the lobe measure or something. You sort of run into minor but non-trivial technical complications making that stuff about cardinality precise. And the other way to do this, is to just work in a finite setting and say that small means a small finite number. And the trade-off is then you have to really be careful about which quantities are bounded by which. So, formally the theorem would be like there's a function, so that for each d and epsilon, if the VC n dimension is at most d, you need at most u of d epsilon cylinder intersection sets. So small in VC dimension is telling you how many intersection sets are there in this finite union. And so it's sort of a matter of taste which of these you prefer. I'm going to try to split the difference by just using the word small and sort of not worrying about either of the technicalities. All right. So first of all, I should actually tell you with a little bit of care, what is this pre-existing result about VC dimension that we were generalizing? So first of all, reminder, what is VC dimension? So when E is a binary relation, so E is a subset of X cross Y, well, let me say it this way. The VC dimension is roughly the smallest D with the property that there's a bipartite graph. So there are finite sets V and W, and there's a set of pairs in VW, but you can't find a copy of this bipartite graph inside E. And if there's no such D, then the VC dimension is infinite. And as I think many people here will immediately look at this and go, this is not the definition of VC dimension. But okay, so this number D is finite. There's a function that relates bounds on this number D to the actual VC dimension. And this turns out to actually in some ways be a nicer way to define it. I think in the worst case, you can have an exponential gap between this number and the actual VC dimension. But anyway, this definition is symmetric, which the usual definition isn't. All right, so certainly within this realm where we're only worried about the difference between small VC dimension and large VC dimension, this is a good enough definition. So the VC dimension tells us what is the smallest bipartite graph we can't find. And for just one example, so the half graph, right, that's the structure which we could think of as the subset of the unit interval across the unit interval, which picks out the ordering. So it's the set of pairs x, y, where x is less than y. Right, so this is the half graph, right? If you sort of draw it as a picture, it's going to be a filled in triangle, and then the other half of the box is empty. And here's a bipartite graph. It has two vertices, x1 and x2 on the left, and two vertices, y1 and y2 on the right. And there's no copy of this in the half graph, because of course, if x1 is adjacent to y2 but not to y1, that had better mean that y1 is less than y2 in this definition. But then x2 thinks that y2 should be less than y1, and these are inconsistent. Okay.
So Henry, you're assuming that there is a label a prior label in the original set E? Because you can find a copy of this graph in the half graph just by moving a little bit the x and the y's, right? So if I just put like x1 and y10, let's say, and x4 and y5, I'm going to have a copy of this graph that you're mentioning. You see what I'm saying?
I don't think you should. Let's see. No, so let's say, so I should say it has to be an induced copy. So you have edges where there are edges and non-edges where there are non-edges. Right, so if
Okay. Yeah.
Oh, okay. That's
Okay.
yeah.
That will explain it. Yes.
Okay. Yeah. Very important that we're talking about induced copies. Yeah. So that
Thanks.
So very importantly, when I say we have no copy of it, I mean that exactly x1 and x2 and y1 and y2, so that x1 is adjacent to y2 and not adjacent to y1, and x2 is adjacent to y1 but not y2.
All right. Thanks.
All right. So this is VC dimension, and I said this already, but I'm just going to stick in the partite setting for everything, and nothing really changes in the non-partite setting, except suddenly you have to spend a lot more time stopping after every line and going, wait, was that symmetric? Does it matter if that's symmetric? Just easier to say things in the non-partite setting. All right. So there's this result. I'm attributing it to Lovász and Szegedy and maybe others, because the version I know got written down in Lovász and Szegedy, but so it's a fairly easy theorem from the general theory. Like if you just know the general theory of VC dimension, it's a short argument, and they wrote it down and they didn't even bother to say it very explicitly, because it just sort of fell out of general things they were doing. And so it may well be in the literature in other places. This is not. So the theorem is relations with small VC dimension are approximately unions of rectangles. Right? And so that's the statement here. If you have a binary relation whose VC dimension is D, and we're thinking here about X and Y as being finite sets, then actually there's a union of rectangles, right? A union of AIs cross BIs that's very close to E. And the number of rectangles you need is actually roughly polynomial in 1 over epsilon, in the equality of the approximation, with the degree of the polynomial depending on the VC dimension. Okay, so one, it's often useful to think about this as saying things with small VC dimension are almost unary relations. They're approximately equal to some other relation which is just built up of unary parts, right? Things where you have an AI and a BI and they don't interact. And because this will come up again, I'm putting the bounds here just to mention that the number of rectangles you need it's a polynomial. It's a small number in epsilon. And this is sort of how many rectangles you need is a natural question to ask. And we'll come back to it again. I want to ask about the converse. So what if you have this property that you can be approximated by a small number of rectangles? Does that mean you have small VC dimension? And the answer is obviously no. And by obviously, I mean that there are structural features that if you're paying attention to them, they should tell you there's no way that could be the case. And then you have to think about how do you actually prove that. And the idea is VC dimension is a combinatorial property. It's about the presence or absence of finite configurations. Whereas this approximation property is fundamentally measure theoretic. Right? I haven't talked explicitly about measures, but I'm talking about all these ratios of sizes that are fundamentally about densities in these sets. And you really shouldn't expect an equivalence between, an exact equivalence between properties like that. And to make that formal, here's the problem. Take a relation on a very large domain, which has small VC dimension, and then add in take the disjoint union with some relation that has pretty large VC dimension, but on a much smaller domain. Well, it's still approximated by rectangles because this extra thing you've added didn't change what happens when you try to approximate it. But you've now changed the VC dimension, right? So you can change the VC dimension without changing the density behavior. And this is why you don't expect the measure theoretic and the combinatorial stuff to line up. There's an almost, but you can fix that. So there's an equivalence if instead of talking about the approximations, you start talking about uniform approximations under any measure. So this is where you get the converse. If you have a relation E where, well, let me say it the other way. If E has large VC dimension, then you can define a measure which concentrates on the part with VC dimension. So if instead of talking about just the density, you talk about like a weighted density and you put all the weight on the part with high VC dimension, then you will fail to be approximated by rectangles. All right, so there is an equivalence. You just have to get, you have to get this uniformity right. But this is actually nice because it helps us get the right statements in some other cases where the exact statement is harder to see. So people sometimes call this result like VC graph regularity or NIP graph regularity, because it can be this approximation by unions of rectangles looks like what happens in Seminario graph regularity. So just to put this result in a little bit of that regularity context. So Seminario is thinking about graphs, which are fundamentally binary relations, and he's thinking of partitioning the space into rectangles. So E is a relation on X cross Y, and you partition X and Y into the union of the AIs and the union of the BJs. And then you look at how does this graph behave on each of the AI cross BJs, on each of the rectangles. So I don't have a good setup for drawing right now, I'm afraid. But if I were on a chalkboard, I would be drawing a square, and then I would be dividing it up into a bunch of, into a bunch of rectangles. And you should have this picture in your head. And so what graph regularity, what Seminario's original regularity lemma says, is that you can find a partition so that on most of those rectangles, but not all, E looks quasi-random on that rectangle. I'm not going to define what quasi-randomness is, but that somehow E looks random in some formal sense. Small number of components here is Tower exponential. So small is a relative notion. All right. So to compare this to this thing I'm calling VC graph regularity, Seminario regularity is for an arbitrary graph. So if instead of an arbitrary graph, you had a graph with small VC dimension, instead of most rectangles being quasi-random, on most rectangles, the density is either close to 1 or close to 0. So these quasi-random things, they could look like the random graph with density 1/2, or the random graph with density 1/3. Like they could do any random thing. If you have small VC dimension, the quasi-randomness becomes moot, because either on each of these rectangles, you're either most of the points in that rectangle or almost none of them, except for a few rectangles which might be exceptional. If you think about the half graph, which I said has small VC dimension, but and if you take that, take your rectangle, divide it down the middle, and divide it along the diagonal, so the top half is all E and the lower half is not at all in E. And so you've got these two triangles. And then if you divide it into rectangles, most rectangles are in one part or the other, except along the diagonal, where your diagonal line will cut right through the rectangles in the middle. All right. So I think people started calling this VC graph regularity really after Malliaras and Shalah's stable regularity lemma, right? So if E is not just small VC dimension, but stable, which in particular rules out that half graph example, every single rectangle can have density that's either close to 1 or close to 0. And just to sort of complete the picture, Chernikov and Starshenko proved that if E is distal, then most of the rectangles are either the whole rectangle or none of it. So not density close to 1, but literally every single point is in your relation. Artem pointed out to me at some point that one of the nice, right? So distal is supposed to be this sort of things that are small VC dimension, but not stable, like the other side of it. And one sort of illustration of that is that if you had something that's both stable and distal, you could hope to combine these two results, and you'd get a partition in which every rectangle was either the whole rectangle or none of the rectangle, which is to say you're just a finite union of rectangles, which is to say if you're both stable and distal, you're kind of trivial, which is exactly what the sort of model theory would lead you to think should happen. Okay, so this is the sort of family of results that this VC graph regularity lives in. Okay. So let me finally start talking about hypergraphs, since that's what this is supposed to be about. And let's take the simplest kind of hypergraph, namely ternary relations. What if instead of x being a subset of x cross y, x is a subset of x cross y cross z? All right. So Chernikov and Starchenko showed, well, if you have small VC dimension, because there is a definition of small VC dimension for ternary relations, then in fact you are still a finite union of rectangles. And here a rectangle is of course a ternary product. I'm writing this in sort of very abbreviated notation. Small VC dimension then E is approximately equal to, but I mean exactly the same kind of approximation statement from for some reason, well, I sort of know why, but the theorem they prove in their paper is weaker than it should be, because they use an unnecessarily restrictive definition of how to generalize VC dimension. So there are two ways you might generalize VC dimension to ternary relations, and people tend to use the wrong one. So one way you could do it is you could think of a ternary relation as being a binary relation, say between x times y as a single set and z. Or you could think of it as a relation between x times z and y. So there are these three ways of thinking of it as a binary relation. And so you could say small VC dimension, or the VC dimension of a ternary relation is like the maximum of those three VC dimensions. So small VC dimension means each of these three ways of viewing it as a product gives you small VC dimension. But for these, at least for these regularity type results, that's actually too strong. So there's a weaker notion, which is you could ask that you could think of this, get binary relations by looking at the slices. So this ternary relation, if you fix an x, it gives you a binary relation, namely the set of yz such that xyz is in E. So you could take the supremum of the VC dimensions over all the binary slices. So all the things you get when you fix one x and when you fix one y and when you fix one z. So it turns out this is a, let's see, so this is a less restrictive notion. So it's easier to have small VC dimension in this sense. But this is nonetheless enough to give Chernikov and Starchenko's result. And furthermore, that's not the next slide. Furthermore, that's the definition you want because that's the definition that gives you the converse. So if you have small, if you are uniformly approximated by small rectangles under every measure, then these slices have small VC dimension. But you're not actually guaranteed that you have small VC dimension in this stronger sense. Okay, anyway, that's enough about that. So there is this way of generalizing the binary result to the ternary result. The proof is similar with just a little bit more work. But this is a little bit incomplete. First of all, for a ternary relation, for relations that are more than binary, small VC dimension is actually a very strong assumption. These are not the most natural examples. And that approximation by rectangles, this would be the analog of what's called weak hypergraph regularity. So weak hypergraph regularity gives you some kind of approximation by rectangles. And there's a theorem about which I will say a little, though not fully state, because it would take the rest of the talk to state it in any detail. But there's a full hypergraph regularity that's much more difficult to prove than weak hypergraph regularity. And it's not analogous to this approximation by rectangles. Full hypergraph regularity doesn't just look at rectangles, it looks at cylinder intersection sets. So this is one of those terms from the theorem at the beginning that I owe you a definition of. So the model of a cylinder intersection set is a set that looks like this, a set of XYZ, so that XY belongs to U and XZ belongs to V and YZ belongs to W. So I like to think of these as ternary sets that are somehow defined by binary sets. Right? This ternary thing is defined by 3 pairwise properties. So the term comes about because a cylinder set would be like U cross Z in this example would be a cylinder set. And then a cylinder intersection set is an intersection of cylinder sets, which is a perfectly reasonable thing to call that. I often like to sort of think of these sets as follows. I like to imagine, what if we were going to play a game where we had a ternary relation, XYZ, and you secretly picked an element XYZ, and I was trying to guess whether XYZ was in the set or not. And I get to ask you questions, but I'm not allowed to ask you just any questions. I can only ask questions that use about 2 points at a time. So I can ask you, is XY in this set? And you would answer yes or no. And I could ask, is YZ in this set? You can answer yes or no. But I could never ask you about XYZ altogether at once. Okay. So if you follow the narrative so far, right, we started with VC graph regularity, and we looked at this generalization and we said it doesn't line up to hypergraph regularity. And so then we asked, what combinatorial property, what should be the analog of VC dimension that lines up with approximations by cylinder intersection sets in an analogous way? And conveniently, sitting in the literature from actually surprisingly recently in some ways is Shalah's VC2 dimension. Shalah calls it NIP2, but we're preferring the combinatorial terminal, right? So many of you know this, but right, so NIP was developed in the model theory world, and VC dimension actually ultimately comes from machine learning. VC is Vopnik-Chernevenkis. And then eventually, I think it was Liskowski realized that actually these are the same thing. And model theory is not unique in this. This notion has been invented maybe 4 or 5 separate times in separate fields because it turns out to be a natural notion. So the model theorists often talk about NIP, and the combinatorial world talks about VC dimension. Okay, so Shalah defined VCN dimension. VC1 is ordinary VC dimension, and I'll just tell you what VC2 dimension is. And again, I'm going to cheat and give this equivalent definition that's a little more natural to state in this context. So if I have a ternary relation, the VC2 dimension is approximately the smallest d, so there is a tripartite hypergraph, which I can't find an induced copy of. So this is exactly the generalization of the binary version I gave you before to ternary relations. So my VC dimension is, in particular, my VC2 dimension is small, means there's some small ternary hypergraph that I can't find an induced copy of. And I can give you my favorite example to illustrate this. So here's an example of a hypergraph that sort of exactly illustrates what's going on at this level. So X, Y, and Z, let's take them to be large finite sets. I'm going to pick random graphs. So I'm going to pick a U that's a graph on XY, a V that's a graph on XZ, a W that's a graph on YZ. And I'm going to pick them uniformly at random, right? So I really mean, I just, for each pair if each pair XY, I flip a coin And if it's heads, that pair goes in U, and if it's tails, it doesn't. And I do that for all three of them. And then I define my ternary relation to be the set of triples x, y, z, so that an odd number of pairs are in the corresponding graph. So first of all, this is approximated by two airy cylinder intersection sets, right? You can sort of write them, think about how to write them down. It's going to be like, well, if I'm in U and the complement of V and the complement of W, or if I'm in V and the complement of U and the complement of W. So you can write down like 4 cylinder intersection sets, and I'm a union. However you're going to define it, E has high ordinary VC dimension. And the reason is that U, V, and W are random graphs. So they're sort of a canonical example of something that's IP, that doesn't have small VC dimension. So it very much has large VC dimension, but it has small VC2 dimension. And I expect to, sometimes this is, in some framings, this is very easy to see, and actually set up like this, it's sort of very nicely easy to see. So consider the hypergraph. So you have 3 parts. Each part has only 2 vertices. So there are 8 possible hyperedges, right? 8 possible sets of 3 elements, where the first is from one of the first, right? You pick with one element from the first 2 points, one element from the second 2 points, one element from the third 2 points. And consider the hypergraph where you have 7 of those 8 hyperedges present. Then you have no copies. And you can just do this by adding things up mod. If you just add up mod 2, what has to be happening? You get something impossible, right? If I tell you that 7, so my vertices are xx prime, yy prime, zz prime, and I tell you that everything other than x prime, y prime, z prime is present, and if you just add up all the characteristic functions mod 2, you get a contradiction. So the way I've defined it, this means I suggested the VC dimension. This means the VC2 dimension should be 2, because there's a graph with, each of these sets has size 2. I think in the usual definition, it's actually like 65. So there's just a slight gap in the numbers between the two, between this definition and the standard definition. But it's a finite relationship. Like if one of them is finite, the other is finite. You can compute you can write down explicit bounds. Like if you know a bound on one, you get a bound on the other. And this definition is somewhat easier to state, in part because actually the numbers are so much smaller. Okay. So let me say our theorem again, now that we've given it some context. So if I have a ternary relation with small VC2 dimension in exactly this sense, then I have a small number of these cylinder sets given by ui's, vi's, and wi's, so that E is approximately a union of the cylinder intersection sets corresponding to these. Right? I can write E down as a small union of sets of this form. And then I can say, well, the generalization is just, the full theorem is exactly this for where E could be a relation of any arity, and we have any bound on the V, and any of the VCN dimensions is small. And you can, in general, talk about VCN dimension of a K-airy relation, again, by sort of looking at slices in the way I talked about it. Okay, so I want to talk, well, I have a little more to say about how we prove this, though not in detail, but I want to pause here to say, this is the result, and I hope the website gives some context for why we were looking for this and why we thought it should be true. I can pause if there are questions about things I've said so far.
I do have a small questions
Yeah.
about the different definitions of VCN. So, I mean, I'm not sure if I understand correctly, but basically the definition that you gave with hypergraphs, what you are saying is that it is finite if only if the other one is finite, right?
Yeah.
And that probably there is an exponential relation between the two of them.
Yeah.
Right. But do you? I mean, the question is, do you know explicitly what is that exponential relation? I mean, is it like the relation between, I don't know, BC dimension and BC dimension of the opposite formula or something like that?
It might be slightly worse because I think you might need to use. So first of all, I should actually say I'm not sure the best bound is known, and that's maybe a question. So the issue is the way I know to get from one to the other actually involves Ramsey's theorem and Ramsey's theorem for k tuples. So the bounds will not be good.
Mm-hmm.
And it's going to be and as a result, the argument is, well, not that much more complicated, I guess. But it might involve multiple exponents or something.
Do you know if it's written somewhere, perhaps?
I don't know. I haven't. The only place I can think of where it might have come up is so there's this paper by Chernikov, Palanchine, and Takeuchi that and it's not directly on VCN dimension, and
I guess that's about independent theories, right?
That's about independent theories, and they're proving sort of the analog of the Sawyer-Shella theorem for independence. And they may go through this characterization, and because they're dealing with explicit bounds there, and so they may sort of incidentally have written down bounds for it. But I think that's the only place it would have actually been written down.
Okay, thanks.
Yeah. So by the way, one of the sort of implications here is VCN dimension. So this happens actually a lot with these higher arity generalizations. So Seminario proved graph regularity in, I think, 69 or something like that, give or take. And hypergraph regularity isn't proven until basically 2000. When, by the way, is as these things happen, proven by like 3 different groups simultaneously. And similarly, I mean, VC dimension and NIP theories have been around for a while, and Shella wrote down this definition of VCN only in like 2001 or something. And in retrospect, it's not really clear to me why. Like, it just took a long time to people to start considering these higher arity things, and they're always a little bit more complicated. But in particular, like VCN dimension, there have been 3 or 4 papers on it total, and there's a lot of kind of basic stuff that isn't known. And one of the points one of the points of this is one of the sort of fundamental result, it's one of the things we should really expect to know about VC dimension and about VCN dimension. It was missing, and there's a lot of basic stuff that's still missing about VCN dimension. All right. Oh, let's not worry about that. That's just the same thing with more symbols. Okay. So I want to talk just in the last, I assume I should go till about 9:50.
9:50 will be fine. Yeah, sure.
I thought with the last bit, I'd talk a little bit about the proof. There are reasons I don't want to go into great detail in the proof. So in fact, what I want to tell you is why I'm not going to go into detail in the proof. So let me first of all tell you about VC graph regularity. So I said that this was sort of so easy that it had almost no one had really claimed credit for it. And the reason is because it follows almost immediately from 2 sort of standard facts about VC theory. So the first is the thing that is called the VC theorem, which is, it's like the fundamental theorem of VC dimension. So when you have a set with finite VC dimension, and you take a large subset y0 of the y coordinates, every single x either is in one of the EYs you've picked or is in very few y's. So we call this set y0 an epsilon net. And because you think of the y0s as like a net that can catch the x's, right? Do we catch one of the x's in an EY? And the answer is we do unless EX is tiny, right? So we have these holes of size epsilon that x's can get through, but otherwise we catch all the x's. And the second thing you need to know is that when a graph has finite VC dimension, so does the following symmetric difference graph. The set of triples x, x prime, y, so that y is in the symmetric difference of EX and EX prime. And once you know these two facts, you say the following. You take an epsilon net for the symmetric differences. So for each x and x prime, either EX intersect y0, if, clearly my calendar was off. If EX, so think through what the definition of an epsilon net means for this symmetric difference. If this EX intersect y0 is equal to EX prime intersect y0, that means the symmetric difference of EX and EX prime is not caught by anything in y0, which means the symmetric difference had size less than epsilon. But there are only finitely many subsets of y0. So you partition the x's into finitely many groups based on which subset of y0 they pick out. And then you just pick one representative for each of those groups. And each EX, each fiber is within epsilon of this representative fiber XS you've picked out. Furthermore, I'll add the Sawyer-Shellow theorem, which is the other main theorem about VC dimension, tells you actually only have polynomially many of these, right? So this argument that I've just given you tells you that it's like exponential in the size of the epsilon net. And then you use the fact that epsilon, there's the y0 need only be taken polynomial, and furthermore, only polynomially many of these PSs actually are represented. But never mind the quantitative details. Right? You take this epsilon net on symmetric differences. All right. So, and the key intermediate step, right? This sort of the key thing you go through is what we call this epsilon net on symmetric differences. When E has finite VC dimension, I can find a small number of x1s through xn's, right? These are representing those, right? xi represents a subset of that epsilon net y0 in the previous slide. But I can pick these representative x's, and every slice EX is close to one of the EXIs. Right? This is sort of the key thing you get out of that argument, and then you can use that to build that representation as a finite number, as a union of rectangles. And the key step in our proof is proving an analog of that. So this is the analog of approximations by fibers, which is very slightly more complicated. So if E has small VC2 dimension, there's a finite sequence of x's. So x1 through xn give us these representative slices EXI. And these are now graphs. They're binary relations on Y cross Z. All right, so what is this saying about this? This is not saying that every EX is close to one of the EXIs. So what is this saying? This is saying that if I take an X, I want to approximate EX. I want to describe the fiber EX using the EXIs. What I'm promised is that I can divide Y cross Z into rectangles, right? That's this Y is a union of the B's and Z is a union of the C's. So I can slice it up into rectangles. And on each rectangle, EX is close to, well, not one of the EXIs, but some element of the Boolean algebra generated by the EXIs. Okay, so first of all, the fact that like the EXIs aren't enough and we have to instead take, you know, the unions and intersections and complements and get the finite Boolean algebra, that's kind of a natural generalization. And you don't need that complication in the binary case, but that turns out to really be what morally you should have wanted. The new complication is this: you don't get a single approximation of EX. Instead, each value X gets its own partition of Y and Z. And then you can somehow, on each piece of this partition, approximate EX. Okay. So this is a much more complicated lemma. This is, 90% of the work is proving this lemma. And as I'm sort of trying to suggest, well, let me point out, so once you have this, you can sort of see how you're going to write down your cylinder intersection sets, right? The EXIs are subsets of Y cross Z. These partitions, the B's and the C's, if you take them over the X's, you get a subset of X cross Y and a subset of X cross Z, and then you can take this configuration and assemble it into a union of cylinder intersections. So once you have this, you don't have much work to do. But the proof of this lemma is substantially more complicated. We argue that, well, if you don't have this, then we do a sort of complicated indiscernibles argument, and then a lot of messing around with tail measure spaces to argue that somehow this leads to a contradiction with small VC two dimension. In particular, the main point I want to make is this is a much more complicated proof than the binary case. So let me leave it with two questions. How many cylinder sets do you need? For VC graph regularity, it's polynomial and epsilon. We actually think the bound might not be terrible. I just said we use a bunch of indiscernibility arguments, which should not lead you to be optimistic that it's good. But we use indiscernibility arguments in a probabilistic setting that might be stable. And Ramsey's theorem for stable theories has better bounds. And so there's some hope, but it's a complicated argument, and it's not clear what the bounds would be. And it would be a fair amount of work to figure them out. But the other question is, in general, what else that we know about VC sets generalizes to VCN sets? In particular, one of the things that makes our proof very difficult is we don't have an epsilon net theorem. We don't have an epsilon net conjecture. It's not at all clear that there is a definition of epsilon nets for VCN sets. And so a lot of the work in the proof is the fact that we have to go through this much longer path to prove this, that we have this small number of approximations, because we don't have any analog of the VC theorem. So this is, to me, actually the outstanding question. What would an epsilon net for VCN sets even be? Or barring that, can we actually find some way to prove that there is no analog? I'll stop there.
Okay, well, thank you very much, Henry, for the talk. Is there any questions from the audience?
If nobody else is talking, I'm going to ask a really naive question.
Go ahead.
And that's, I just don't grasp what's going on when we go from VC to VCN. Because when I start off with the basic definition of the independence property, I'm dealing with n-area relations. And so why do you know, what's happening now that you need to say it's a binary relation or it's a ternary relation?
I don't. What definition of the independence property are you thinking of?
You take a formula in 2n variables, and it has the independence property if if you can build a tree.
Ah, yeah. So I'm thinking of the combinatorial.
I'm sorry. I see.
Yeah.
It's that it's in two n variables, and it's the two that's the.
Yes. Yeah.
Okay. Thank you. So.
Okay. Any more questions?
But following up a little bit on this question, so is there some kind of a split between the combinatorially, extremely combinatorially motivated questions that you have been discussing, and also in this work of Chernikov and our people, and a pure multi-theoretic motivation? So that somehow some properties are not really multi-theoretic, but are essentially combinatorial in nature. Kind of, you're trying to follow up on John's question.
Yeah, I don't think so. Like, I don't think that's the perspective. I mean, I'm not really a model theorist, but Artem certainly is, and I think Artem certainly thinks of this as doing model theory.
Yeah, but
I actually think the motivation is, or at least from my perspective, the motivation here is that actually I think on this one, the combinatorialists actually got a little bit ahead on, like, hypergraph regularity was kind of the first thing. And I actually see this about really going, okay, we know what works in that setting. How do we import that? What is that telling us we should be looking for in the model theoretic world? And so I think, answering these questions about how things, so answering questions about like what's the analog of regularity stuff here is a piece of trying to figure out what should NIPN theories, and how do you generalize more traditional model theoretic things about NIP theories to NIPN theories? And I think these are related. I think I'll just add, I think we have some sense that stability and NIP are qualitatively different dividing lines because they're characterized by these sort of finite induced substructure properties, or finite induced relation properties. And that seems to give them that sort of gives them a particularly combinatorial flavor in a way that none of the other dividing lines seem to have. And that makes them kind of particularly amenable to this generalization.
Yeah, that's a very interesting point. Yeah, the other dividing lines seem to be more, about global behavior of something, or long chains, or trees, and these two, they have this, very small, finite combinatorial flavor. And I can think of maybe John knows some other variants of.
Well, I mean, which are the ones that? What are you contrasting it with?
I compared to, say, simplicity or SOP or TP.
Yeah.
So what I don't understand. Yeah. So simplicity, but SOP seems to me to be exactly the same character.
So SOP, I don't, because you can't actually characterize it in terms of just in terms of finite excluded subgraphs.
Because there you have a tree property, and it's an infinite tree property.
Yeah,
it is also combinatorial, but not in the same.
No, I mean it's not. I mean it's certainly. I mean it's the same thing of you need to have arbitrarily large finite structures, but it's true that it's not. It has to actually be linearly ordered instead of just being a representative of the linear.
Right.
I see there's a difference there, right?
Yeah.
But it's not the cardinality.
No, it's not. Yeah, in that case, it's not the cardinality. It's the kind of restriction you're putting on it. And yeah, and I think so. It's just less clear exactly how some of these things will generalize. Whereas stable and NIP, there's a cleaner generalization. And Artem, I know Artem has thought about, and I mentioned I think there's a grad student somewhere who's thinking a little bit about like what might n-ary generalizations of distality be. Like, I mean, it's not there's not necessarily only for NIP instability, but there's sort of very natural places to start with this because they're so explicitly combinatorial.
Okay, well, are there any more questions for Henry? Well, if there are no more questions for Henry, then let's thank him again.
Thank you.
And just a reminder, we will be restarting next week with the talk of Nicolás Najar from Universidad Nacional. He will be talking on Wednesday, 4 p.m. Colombian time. And yeah, the title is still to be announced. So.
Okay.
Thank you very much. Goodbye.
Thank you.
Thank you.
Thank you.
Yeah, thanks, Henry. Very nice.
Thanks. Great talk.
Thanks.